Hello. So in our previous video, we started to learn how to write a simple direct proof, and we had one definition, well maybe two, that we knew. The definition of an even number and the definition of an odd number. Today we're going to continue our study of practicing how to write direct proofs, and we're also going to sort of generalize that definition of evenness to, in general, divisibility. So what we're studying right now, we're doing two levels. We're learning how to think with definitions, and the definitions we're learning to think with come from the area of number theory, which is the study of the integers. So we're going to think really carefully about how the integers work, sort of when we do arithmetic. Okay, so these are our learning objectives. We're going to understand the definition of divisibility, understand what it means for two sets to be equal, and learn how to prove that one set is a subset of another. Okay, so the new definition for today is divisibility. So if A and B are both integers, we say that A divides B, and we write this A bar B if there exists an integer C such that B is equal to AC. So this should remind you a lot of the definition of an even number, right? For an even number, if you have an even number, that A is equal to 2. So here, A is equal to 2 for even numbers, right? And then we get the equation that B is equal to 2 C. Oops, I'm just trying to erase this little dot I made. Okay, right? So this is a generalization of the definition of evenness. So evenness is if a number is divisible by 2. And so now we're saying, well, what if an integer is just divisible by some other integer A? And I want you to see that using this definition, it works just like the definition of evenness. So let's see. I want to grab this thing. Oh wait, maybe I'll grab it over here. So I haven't done this before. I'm screen sharing over there, but I think I can move this claim. That's right, right here. I'm on two devices at once, guys. I'm on a desktop for Zoom and the iPad for this. All right, so I want to do an example to show you that the definition of even and the definition of divisible work very similarly. So this is the generalization of the claim that we proved in the first video, that if m and n are even, then m plus n is even. So here we're proving if m and n are divisible by a, then m plus n is divisible by a. So let's prove this claim. Again, we're going to signpost where we think our proof is starting. And we're going to follow that direct proof poem, okay? We're going to write down what we want to show. We're going to use what we know, which in this case is the definition of divisibility. Then we're going to do a short computation, and then we're going to finish by writing down an interpretation of that computation that is a conclusion for us. And we're going to do it all in paragraph form, okay? And all of our computations will appear inside of sentences, even if they're sort of out of line, right? They're not in line. Okay, so let's get started. I'm going to start by writing down what I know, which is from the definition. So I might start with since, or maybe I'll start with let. Let m and n be integers that are divisible by a, and then I'll say, therefore, by. Now, if I were writing this for homework, I wouldn't write shortcuts, but sometimes when I'm in class or writing on the board, I'll use abbreviations for words instead of writing them full out. Therefore, by definition, there exists integers, and I have to give them different names now, maybe K and L, and I have to give them names and tell you where they live. Okay, they live in the integers. Such that, and so now the definition is going to give me two equations, and I'm going to use those equations inside my computation. Okay, so such that M is equal to AK and N is equal to AL. All right, so now I have to do a computation, and I have to remember I have to put that computation inside of a sentence. So I'm going to do since. I'm going to know where I'm going in advance. Okay, so I'm going to say since. So since I want to make a conclusion about M plus N, so that's what I want to compute. Since M plus N is equal to AK plus AL, and that's, now I'm going to factor out the A. So since M plus N is equal to AK plus AL, and that's equal to A times the quantity K plus L, comma, and K plus L is an integer, comma, by definition, A divides the quantity M plus N. And we're done. Okay, so if you look back in the at the notes from the other video and see how we proved that if M and N are even, then M plus N is even, this is really the exact same proof. And then you can go back and you can say, wait, you know, all the things we proved about even numbers, you can ask yourself, you can do this wondering kind of question, right? You can say, I wonder how many of these things are true for the statement, like if using the definition A divides B, right? And you can go, oh, wait. And then you can get a whole new bunch of claims and lemmas and theorems, right? And this really is how math is discovered and how research goes, right? You do one thing and then you say, wait, I think I can do that more generally. And you say, oh, I wonder how many of those things that I did are still true in this more general situation, okay? So now you've seen the definition of divisibility, and you can guess that if you want to sort of think about how to write a direct proof using this kind of definition, there are a whole bunch of things you can try to prove now. Okay, and these proofs, while they seem really maybe like small facts, when you put these facts together that we're proving in class, they're really telling you something about the structure of the integers, okay? And you'll see later on, if you take abstract algebra, oh, these are the things you need to prove to really understand this the algebraic ecosystem of the integers, okay, and their variance. So I also want to tell you about what it means to prove that two sets are equal or that one set is a subset of the other. So for this, I want to think of, we sort of have to learn a new proof technique. And this is the idea that what it means for two sets A and B to be equal is that A is a subset of B and B is a subset of A. Okay, if A is a subset of B and B is a subset of A, it means that they have exactly the same elements. All right, so what we really need to do then is think, well then, how do I show that one set is a subset of the other? And in general, what you do is you take an arbitrary element of the one set and show that it's in the other. What does that mean? Let's do an example. Okay, so I've set up this example for you. I want to show that these two sets are equal. So one of them is the set of all integers that are divisible by 6. And the claim is that the set of integers divisible by 6 is equal to the intersection of two sets where one of those sets is the set of integers divisible by 2, and the other is the set of integers divisible by 3. Okay, so let's see how we might prove this. This is going to involve 2 proofs, okay? So we're going to signpost that our proof is going to start, and when you're trying to show that 2 sets are equal, you have to show that the left-hand set is contained in the right-hand set and other vice versa. Usually you do that in at least 2 different paragraphs, and you signpost which one you're doing, okay? So maybe in parentheses, maybe I'll just start with a sentence and I'll say that we'll begin by showing that the set, and you know what, this is gonna be, well, I'll just write them out. I was thinking of using letters, but we'll write it out. The set of all A integers such that 6 divides A is contained in the intersection of those 2 other sets. Okay, here we go. All right, so how do I do that? Well, I've got to take an arbitrary element of the set on the left. So I'm going to say that now I really am going to give them names. I think I need to give them names. And maybe, you know what? Maybe I should have done that from the very beginning. I'm going to erase this and restart. And this is the kind of thing where I want to do this for you because, and not restart the video, because sometimes you have to backtrack and you realize, whoa, I'm going to be writing all this stuff over and over again. And this is like a proof. Take note of this. If you find yourself writing a big complicated thing in a proof over and over again, that's a good sign that maybe you want to replace that big complicated expression by a letter or a shorter name, okay? You don't want to go overboard with lots of new terminology, because it's like increases the cognitive load on your reader, but it also increases the cognitive load on your reader to read really complicated expressions over and over again. So it's a judgment call that you're going to have to learn to make. All right, so I'm going to make that judgment call here though, and I'm going to say, oh, I keep forgetting that. I'm going to say, let A be the set of all integers divisible by 6. B be the set of all integers divisible by 2. And C be the set of all integers divisible by 3. All right, so I'm going to show, now in my second paragraph, I'm going to say, first, we'll show that A is a subset of B intersect C. And I think that's more readable than writing out the long sets, okay? So to do that, I start by saying let A be an arbitrary element of A, okay? And now I'm going to use my direct proof poem, okay? I've written down what I want to show. We'll show that A is contained in B intersect C. The next part of the direct proof poem says, write down what you know. So what I know is that little a is contained in A, and I know the definition of that. So I can say, since little a is in A, we know that 6 divides A, okay? And I might have to, now I have to use what I know, 2 different things that I know, 2 pieces of information are going to appear in the logic of this proof. The first is that piece of information that defines the set capital A. And now the other thing I know is the definition of divisibility. So I'm going to say because I've already used since once in this proof, because 6 divides a, by definition, there exists an integer k, so an integer k, such that, and then I get this equation that says a equals 6k. All right. All right. This is great now because now I'm going to do a tiny computation. That's where we are in the direct proof poem. And so I'm going to take away that period. And I'm going to say 6k is actually equal to 2 times 3 times k. So here my computation is really this tiny thing of factoring the 6, okay? And so I'm going to rewrite, actually I'm going to keep going with my computation. I'm going to rewrite that in 2 ways. That's equal to 2 times 3k, or maybe actually, you know what, I'm going to pause there. I'm going to put the period there. And then I'm going to say, okay, I'm going to say since 6k, or no, since 2 times 3k times k is equal to 2 times 3k, we see that A is in set B, because we've written the little integer A, the integer A as 2 times the number. We've shown that it's divisible by 2. And then here's where you get to use all these words you don't usually use in real life. We're going to use the word moreover, okay? Moreover. Moreover, 2 times 3 times k is equal to 3 times 2k. So A is in C. And maybe here, I should have written because 3k is an integer, because 2k is an integer. Okay, so we've seen, right, that we can write A as 2 times an integer, and we can write it as 3 times an integer. So A is in B and A is in C. Thus, A is in B intersect C, and therefore A, the set, is contained in the intersection of B intersect C. Okay, so this is just, ooh, oh dear, let's see. You can't see some of my screen. I'm gonna stop the screen share. Let's see, and I'm gonna zoom. Whoa. Huh. All right, so the browser, that didn't quite show the whole thing. So this is half of the proof we wanted to do. So showing that A is contained in B intersect C. And I think what I'm going to do is I'm going to leave the other half of the proof, the B intersect C is contained in A, for you to do as part of your pre-class warm-up, and we'll start class with that when I see you tonight. Bye-bye, everyone.